Hey guys, today we're going to look at the remaining theorems regarding polynomials and their zeros. So first we're going to start with the fundamental theorem of algebra. Now this is actually one that we've already been using. The fundamental theorem of algebra states that the polynomial degree, so meaning the highest exponent of the polynomial, will tell you exactly how many zeros you would have. And this includes both rational and irrational as well as complex zeros. Now, the conjugate root theorem states that if you have, let's say, a complex number, such as a plus bi is a root of the polynomial, then its conjugate, a minus bi, must also be a root. And this also applies to irrational roots, such as radicals. So, like, if the square root of 2 is a root, then negative square root of 2 would also be a root. The linear factorization theorem states that if you know exactly all of the factors of your polynomial, you can actually write the linear factorization of the polynomial. Now, what linear factorization is basically all of the factors that create the polynomial. So, for example, if I know that the polynomial has roots 2, -3, and 4, I can write the linear factorization, meaning that 2, the factor that would give us a root of 2 is x minus 2. If we have -3 as a root, then the factor associated with that would be x plus 3. And if we have 4, then x minus 4. And this is found by, like, let's say, for example, the x is equal to 2. To get the factor, we have to make this equal to 0. So we would have to subtract the 2, and we get that x minus 2 is equal to 0, making x minus 2 the factor of the polynomial. And then, of course, you can't forget the other two theorems that we covered before, the rational root theorem and the Descartes rule of signs. So let's actually apply some of these theorems. So first, we're going to use the conjugate root theorem to write the polynomial function with those zeros. So basically, we're using the conjugate root theorem in order to write the linear factorization of that polynomial. So in this example, we have write a polynomial of least degree with real coefficients in standard form that has the roots -2, 4, 3, and 3 minus I, and that satisfies the condition where f of 1 is equal to 90. We'll get to that part at the end. First, let's see if we can actually write out this polynomial. So we have those roots, and then since 3 minus I is a root of the polynomial, so is its conjugate, 3 plus I. So first we're going to start off by writing the linear factorization. So f of x is going to equal to x plus 2, and that's because of the -2. In order to write the factor, you basically just change the sign of the number. Then the other factor would be x minus 4. For 3 minus I and 3 plus I, you can just write x minus 3 minus I and x minus 3 plus I. So this is the linear factorization, but the question is asking to write it in standard form, meaning that we would need to multiply everything out. Now my recommendation, because of those i's, I usually like to get rid of those complex numbers first, because when I multiply complex conjugates, what's going to happen is that the i's will end up canceling out. So I'm going to multiply these two first. So we have the x plus 2, x minus 4, which I'll multiply in a moment, but we're going to first distribute all of this. So I'm going to distribute the x, which would give me x squared minus 3x plus ix. Now I'm going to distribute the -3, which is -3x plus 9 minus 3i. Now I'm going to distribute the -i. So -i times x is -ix, -i times -3 is plus 3i, and then -i times +i is -i squared. So when we look here, what ends up happening is that these ix's will cancel because one is positive and one is negative, as well as the -3i and the +3i. Then this negative I squared, we know that this I squared represents negative 1. So this is negative 1, which is just plus 1. So now let's simplify this a little bit more. So we have the x plus 2, x minus 4. Now we have x squared. Then negative 3x minus 3x is negative 6x. And then 9 plus 1, which is plus 10. Now I'm going to multiply these two together. So we would get x squared minus 4x plus 2x, minus 8. Let me fix that. And then the x squared minus 6x plus 10. We can now combine those like terms. So x squared minus 2x minus 8 times x squared minus 6x plus 10. Now we have to multiply these out. So distribute the x squared. You would get x to the fourth minus 6x to the third plus 10x squared. Now we're going to distribute the negative 2x, which is negative 2x to the third plus 12x squared minus 20x. And finally, distribute the negative 8, and we get negative 8x squared plus 48x minus 80. Now we can combine like terms, and that would be our polynomial. So x to the fourth, then we have negative x to the third minus 2x to the third, which is negative 8x to the third. Then 10x squared plus 12x squared is 22x squared. And 22x squared minus 8x squared is a positive 14x squared. Finally, we have this negative 20x plus 48x, which is a positive 28x. And lastly, the minus 80. So this is f of x so far. Now, it has to satisfy this particular condition that f of 1 is equal to 90. So what we would have to do is plug in 1 and make sure that it equals to 90. Now, for this particular, you can either just directly plug in the 1 and see what you get, or you can also use the remainder theorem, which is what I usually prefer, just because I think it's a little bit easier, which is that we plug in the 1 into the little box, and then we put all of our coefficients, 1, negative 8, 14, 28, and negative 80. Now remember that we're doing this because according to the remainder theorem, my remainder would be my answer if I were to directly substitute. So I bring down the 1. 1 times 1 is 1. Negative 8 plus 1 is negative 7. Times 1 is negative 7. 14 minus 7 is 7. 7 times 1 is 7. 28 plus 7 is 35. 35 times 1 is 35. And we end up with negative 45. So for our polynomial right now, if I plug in f of 1, I actually get negative 45. I don't get 90. But if I multiply negative 45 by negative 2, then I would get 90. So what that means is that we would have to multiply negative 2 to f of x. So we get our function here, and we're going to multiply a negative 2. So x to the fourth minus 8x to the third plus 14x squared plus 28x minus 80. We distribute the negative 2, and we would get that f of x, our final polynomial, is negative 2x to the fourth plus 16x to the third minus 28x squared minus 56x plus 160. and this would be my final answer. So remember, we're multiplying this -2 so that it satisfies that f of 1 would equal to 90. The reason why we do that is because possibly with these roots, remember, if you're factoring a polynomial and you're factoring out a constant such as -2, it's not going to affect the values of the roots. So sometimes we need this additional condition so that way we can determine what the actual polynomial is in case we were missing that constant that needed to be multiplied. Let's try this one more time. It says to write a polynomial function of least degree with real coefficients in standard form with the zeros -1, 1 that has a multiplicity of 2, 4, and 4i, and that satisfies the condition f of 2 is equal to 60. So first, let's write the linear factorization. So we have the 0, -1, so that means the factor is x plus 1. We have the other 0 of +1, so that means that it's x minus 1, but it has a multiplicity of 2, so that means that I have 2 of those factors. And then we have 4i, and if 4i is a root, so is its conjugate, -4i. So our roots would be x minus 4i and x plus 4i. So now we got to multiply all of this out. Now what I do usually is I multiply 2 factors and 2 factors at the same time. And that's just to save on, work and space, etc. So what I'm going to do is I'm going to multiply these 2 first and these 2 at the same time. Now I'm choosing to multiply instead of x minus 1 with x minus 4i because remember, if you multiply the conjugates together, then I will cancel out. If you, not that doing it the other way is wrong, it's just that it's going to get a little bit messier and it leaves room to make mistakes. So I always choose to multiply those conjugates first. So here we go. If I multiply x plus 1 with x minus 1, this is a difference of squares, so I already know it would be x squared minus 1, but let's just say you don't remember that. Just multiply it out, you would get x squared minus x plus x minus 1. And see how those middle terms here cancel out. I still have this x minus 1 here, and now I'm going to multiply these conjugates. X times x is x squared plus 4ix minus 4ix minus 16i squared. These would cancel. And then this negative 16i squared, since I squared is -1, negative 16 times -1, this would become a plus 16. So let's clean this up a little bit. We have now x squared minus 1 times x minus 1 times x squared plus 16. Now we're going to multiply, it doesn't matter the order in which you choose. I'm going to do these two now. So x squared times x is x to the third. X squared times -1 is -x squared minus x plus 1. And now I need to multiply that with x squared plus 16. Distribute the x cubed, we would get x to the fifth plus 16x cubed. Now distribute the -x squared, that would be -x to the fourth minus 16x squared. Distribute the -x, we would get -x to the third plus 16x. And finally distribute the 1, we get plus x squared plus 16. So now what our polynomial is so far. We're going to combine like terms and write this in standard form, starting with our highest exponent, so x to the fifth. Then we only have 1x to the fourth, so minus x to the fourth. Then we have 16x to the third minus x to the third, which would be plus 15x to the third. then negative 16x squared plus x squared would be negative 15x squared. And finally, plus 16x plus 16. So this is what I have now. Now we have to make sure that it satisfies this condition, and if it doesn't, we're going to multiply a number so that it does. So we're going to put 2 in the box, write our coefficients, so 1, negative 1, 15, negative 15, 16, and 16. Bring down the 1. 1 times 2 is 2. Negative 1 plus 2 is 1. 1 times 2 is 2. 15 plus 2 is 17. 17 times 2 is 34. Negative 15 plus 34 is 19. 19 times 2 is 38. 16, oops, this is a negative 16. Shouldn't this be a negative 16x? Oh, I had messed up here. This is supposed to be negative 16x because it's negative x times 16. So negative 16 plus 38 is 22. 22 times 2 is 44. And 16 plus 44 is 60. Since we get that f of 2 is equal to 60, that means that we don't have to multiply anything. This is our final answer. So there must not have been a constant that was factored out at the beginning. So that's writing the linear factorization and then writing the polynomial in standard form as a result. Now we're going to kind of work backwards. We want to find all of the zeros of polynomial p of x is equal to x to the fourth minus 5x to the third plus 15x squared minus 5x minus 26, given that 2 minus 3i is a zero of p of x. And then we're going to write the linear factorization of p of x. So this is kind of like a two-part question. We're trying to find all of the zeros, and then we're going to also write the linear factorization of the function. So we are told that 2 minus 3i is a root. That means that 2 plus 3i is also a root. Now, what did we do before when I gave you a root? We would divide it from the polynomial to then get the depressed polynomial, meaning the answer, and then we would factor from there. However, when you have a complex root, we still go through the same process, but what we do is we divide twice. We divide the 2 minus 3i, and then we divide that answer by 2 plus 3i. So by dividing, we're going to have to use synthetic division. So we put 2 minus 3i in the box, which I know is going to seem weird, but I promise it'll work. And then we're going to put all of these coefficients. So 1, negative 5, 15, negative 5, and negative 26. So here we go. This is where it's going to get a little bit hairy, but I promise it's going to be fine. We bring down the 1. Then we multiply. 1 times 2 minus 3i is 2 minus 3i. Then we have negative 5 plus 2 minus 3i. So we only combine the real parts here. Negative 5 plus 2 is negative 3 minus 3i. And then we have to multiply these two together, but we've done that before. So we have to multiply 2 minus 3i with negative 3 minus 3i, which we have to FOIL. So 2 times negative 3 is negative 6. 2 times negative 3i is negative 6i. Negative 3i times negative 3 is positive 9i. And then negative 3i times negative 3i is a positive 9i squared, which this 9i squared becomes negative 9. Negative 6 minus 9 is negative 15. And then negative 6i plus 9i is 3i. So plus 3i. Combine, 15 minus 15 is 0, so 3i. Now we multiply, 3i times 2 minus 3i. Distribute the 3i, we get 6i minus 9i squared, which this minus 9i squared becomes plus 9. So this complex number is 9 plus 6i. So negative 5 plus 9 plus 6i is 4 plus 6i. And now we multiply 2 minus 3i times 4 plus 6i. Distribute the 2, we get 8 plus 12i. And then distribute the negative 3i, we get negative 12i minus 18i squared. These here would cancel. Negative 18i squared is positive 18, and 18 plus 8 is 26. And see, we end up with 0. But now we have to also divide the conjugate, the 2 plus 3i. And this one will be easier. So the hardest part is the first part. This one here you're going to see is going to work out much nicer, and we won't have to do so much multiplication. So we're going to now, instead of using these coefficients, we use these new ones. So we have 1, negative 3 minus 3i, 3i, and 4 plus 6i. Bring down the 1. 1 times 2 plus 3i is just 2 plus 3i. See, the 3i's here cancel. Negative 3 plus 2i is, negative 3 plus 2 is negative 1. Now we multiply negative 1 to 2 plus 3i, so negative 2 minus 3i. The 3i's here cancel out once more, and we're left with just negative 2. Negative 2 times 2 plus 3i is going to be negative 4 minus 6i. And see how everything cancels, and we end up with 0. So now we have this quadratic, which is x squared minus x minus 2. Now I know this is a quadratic simply because we started off with a quartic function, right? The highest exponent was 4. So when we divide, this answers to the third. And then when we divide again, this is x squared. So we make this equal to 0 and factor. The two numbers that multiply to give you negative 2 and add to give you negative 1 are negative 2 and positive 1. So our factors are x minus 2, x plus 1. We make it equal to 0, and we get that x is equal to 2 and negative 1. So let's write out all of the zeros. We have that x is equal to 2 minus 3i, 2 plus 3i, 2, and negative 1. Then the linear factorization would be x minus 2 minus 3i, x minus 2 plus 3i, x minus 2, x plus 1. And this is our function. So this is what I would be looking for, the zeros and the linear factorization. Now let's put all of this together, all of these theorems that we have been using. We're going to find all of the zeros of the polynomial function, and then we're going to write the linear factorization of this function. So we're starting from the very beginning. We're going to use both Descartes' rule of signs and the rational root theorem. So I know I have to start off with that because I'm not given any roots. I'm not given any of the rational roots. I'm not given any of the complex roots. So if you know nothing about the roots, you have to use the rational root theorem. So first, let's figure out what our scenarios are here for the zeros. So we're going to compare the sign changes so that we can apply Descartes' rule of signs. From x to the third to negative 3x squared, we have a sign change. Then from negative 3x squared to 2x, we have another sign change. And then from 2x to negative 6, we have yet another sign change. This gives me a total of 3 total positive roots, or 1, since we always subtract 2. For negative, we switch all the 1's to 0's, and if we had 0's, we would change it to 1's. But we have only all 1's, so that means that there are no negative roots at all. Now we're supposed to have 3 roots. So if we have 3 positive, we're not going to have any imaginary. But if we only have 1 positive, we will have 2 imaginary. Keep in mind, for imaginary roots, they always come in pairs, and that's because of the conjugate root theorem. There's always the positive version and the negative version. So your imaginary column, if you have any numbers, it should only be even. And that's just a side note. So let's start off with our possibilities here. So the rational root theorem. So we're only going to have positive roots, so we're only going to focus on the positive numbers. All of the factors of 6 would be 1, 2, 3, and 6. Divided by the factors of q, which is just 1. So these are my only numbers here that I would need to worry about testing. So let's start off with 1 and see if that works. We have 1, negative 3, 2, and negative 6. Bring down the 1. 1 times 1 is 1. Negative 3 plus 1 is negative 2. Negative 2 times 1 is negative 2. 2 minus 2 is 0. 0 times 1 is 0. We end up with a remainder of negative 6. So 1 did not work. Let's try 2. 1, negative 3, 2, negative 6. Bring down the 1. 1 times 2 is 2. Negative 3 plus 2 is negative 1. Negative 1 times 2 is negative 2. 2 minus 2 is 0. 0 times 2 is 0. And we still end up with a remainder of negative 6. So 2 did not work either. Let's hope that 3 works. We have 1, negative 3, 2, negative 6. Bring down the 1. 1 times 3 is 3. Negative 3 plus 3 is 0. 0 times 3 is 0. 2 plus 0 is 2. 2 times 3 is 6. And finally, we end up with a remainder of 0. So I'm going to start my list here for my roots. Slash zeros, you know, they're the same. Which is x is equal to 3. That's one of them. Now this here, this is x squared plus no x plus 2. I can't factor this. There's really no way, so we're just going to solve for x. So if I solve for x here, we would have to subtract the 2. And this is so that I could find the rest of my roots. We get that x squared is equal to negative 2. And then square root both sides. We get that x is equal to plus or minus. Now there's a negative inside of the square root. So I make it positive and take out the I. So plus or minus I, square root of 2. So those are my remaining other zeros. Plus or minus I, square root 2. So this is the scenario we ended up having. We have 1 positive and then the 2 imaginary, the positive and the negative version of I square root of 2. So this is the first part of my answer. And now to write the linear factorization. So f of x is going to equal to x minus 3. And then we have positive I square root of 2, so that'll be x minus I square root of 2. And then we have the negative I square root of 2, so x plus I square root of 2. Since remember, when you're writing the factors, you switch the sign of the 0. And this is my linear factorization. And those are the remaining theorems for zeros of polynomial functions.